Okay. Thank you so much for coming. My name is Lee. I would just do a brief introduction. I'm a sophomore. I've been going to Sigma for some times and I watching like record videos and I was really inspired. As like an international student, I feel like one of my most like disadvantages is not knowing how to present my ideas. So that's why I want to actually do this one. And also I'm conducting research on combinatorics and graph theory. So if anyone was interested after like this presentation, I'm really more than happy to hear more of you guys' perspective on my field. So I would start now. What I want to talk about today is probability theory. To be more general, it's doing statistic probabilistic method to prove not just data science statistic, but one of like a really new field is graph theory, where you're using probabilistic method to prove the existence of something. So this is like a small part of how you're gonna prove it. So the parameter I want to talk about today is the concentration inequalities. This is the outline of my presentation. First of all, I will explaining what concentration inequality is, for which is concentration bound. And the three other part is that concentration inequality, there is a lot of result into that. But from my point of view, I divided them into three more smaller like category of how they are, because there are like a bunch of results for its inequalities. So for the easiest and the most basic part is foundation inequalities. The second, a little bit more complicated then, is the concentration inequalities for independent random variables. And the most complex one, from what I can understand, is high dimensional concentration inequalities. So first, I will go to concentration bound. I will explain for you why we need concentration bound. So we all know about expected value. But like how reliable it is for our expected value that we should trust them. Like we don't know. If we just know the distribution and the expected value, we don't know how reliable the results are. So that's why we bring out like concentration bound. So concentration bound is to evaluate how value the expected value is. There is a case that expected value is really worth it. That's when you will use it. But there will be also the cases when it's really not worth it. Two of the most like obvious, two of the most obvious that will like we will definitely not gonna use expected value result is when, for example, uniform distribution, when we know that our x value will be the probability that it's gonna land on our expected value is the same as it will land on any other point. So that's why our expected value, the worth of it is literally none. And even the worst case is when we go into heavy detail distribution, then a heavy tail distribution, that's when our expected value literally worth like negative, because we cannot use it because our expected value is just fall into like a random point. So that's why we using our expected value, we using concentration bound, because the problem is when we using random processes, we never know what distribution we having to face. So that's when we come to this concentration bound. So concentration bound is how it's a parameter, so you can calculate how concentrated it is that your random variable is compared to your expected value. So why do I feel like concentration bound is really useful is because in a complex system, like when you're dealing with machine learning, statistic, or any probabilistic method, you want to guarantee that like the expected value is another word for the behavior that we might expect it to see, right? So we want to guarantee that the observer that we see is not just a randomness, it's actually like useful for your analysis. So that's why this bound is used a lot in machine learning, statistic, combinatorics, and computer science to make sure that your algorithm is right. So I will first going to the most basic part of concentration inequality is the foundational inequalities. So I think you might or might not have heard of Markov, like the Markov model, where you're using uh his model to expect to see to lower your like the range of your variables. So, but and then like another one is Chebyshev inequality, where you using your variance instead of expected value to see where's your x gonna bound into. This is like a two really foundation one, but it's really weak because of Markov is literally just going onto linear, and then and Chef B's is literally just polynomial. When you know that in machine learning, it's a lot more parameter than just that's two simple line. But I still gonna apply it into like one example right here to see why we need concentration bound. So our problem is if you have to do an MCQ true or false question for 500 question, and if your probability of getting it right is 20%, so you know that your expected value is going to be 100, right? But you want 130 to pass. So what is the probability that I can pass? Well, this is basic statistic when you want to find the probability of x bigger than 130. So if you know the distribution, you can easily done it. But in the case you don't know about them, you're gonna use Markov bound as to see it. So Markov bound state that the probability of x bigger than an alpha is smaller than the expected value of them divided by alpha. The proof is pretty easy, but so I don't want to go into it, but if you apply it, you can just change alpha into expected value of x plus t. You plug it in and divided them, and in our case, our x is here, our expected value is this is expected value, and this is our t is 30. And so our chances that we're gonna pass the exam is 0.8. So literally it's really high. But in reality, I don't think so. I did some simulation, but I think you can clearly see that if the expected value is 100, that's like so much more lower than 130, the chance cannot be 80%. So that's why I say that this concentration bound is right, because look, if it's like 5, 7, 8%, it's still lower than 70%. That's true, but the bound is way too high. So that's why we have a better concentration inequalities. That is what I group them into independent random variable. One thing to note is that this is just applying for independent random variable. That's only for random processes. There are concentration inequality outside of this that is for not independent random variable, but it's really much more complex and not really seen much. So I'm not trying to group them into here. So our independent random variable, one of the inequality that I have been using a lot into my research is Matt-Diarmid inequality. If you can, the one thing about concentration inequality is that they have a lot of different inequalities, but there are for different setup. I feel like the hardest part of doing a concentration inequality is how you set up the problem rather than how you solve it. So you have to mind more about like the if statement where you can use it. So Mac-Dermot inequality is you can be used when the bound is different in different condition. I will go into this, so I will explain more about it. And the second one that I also seen a lot in concentration inequality is the Chernoff bound. The Chernoff bound only being used if you have to dealing with a sum of Bernoulli distribution. So I will apply it so we can see more how this is being used. So we're gonna go back to our problem where you're using like a true false question, like the both. So first of all, I'm gonna explain how you can use Chernoff bound. So Chernoff bound is when you have an x1 to xn independent Bernoulli random variable. That is the only case that you can use Chernoff. Then you can divide your cases into two cases, the probability that your x equal to 1 and the probability of x equal to 0. That does not matter. You can also state when xi equal to 1 and xi equal to -1. It does not matter. It just have to be a Bernoulli distribution to say. And it had to be, and then your x have to define as the sum of them. If your setup satisfy these two conditions, then our probability of x bigger than expected value of x
will equal to a constant expected value of x. The bound will be exponent of that constant multiplied with expected value of x divided by 3. You can read more about the proof, but the thing that I bring today is this application of them. So I will try to plug in our problem with this number. So we can see that we want to find the expected value of x minus 100 is bigger or smaller than 30. So our constant here will equal to 0.3 because our expected value is 100. So that's our constant. So on this other side, it will be the exponent of constant is 0.3, the power 2 multiplied with 100 divided by 3. So that is going to be our bounds. So exactly like what I just said, the exponent of this, when you doing the math, it will equal to 0.04. So our chances to pass the test is literally just 4% compared to the bound that we just stated before was 75%. This is so much more effective in a way. Then we're gonna go to McDermott actually I don't know his first name, inequality. So it's also have the name Huef Ding. If this is like the special case of this one is the name for this is gonna be the name for the special. Oh wait, this is gonna be the name for the special case of McDermott. This is only happened when okay, wait, I just gonna explain this first. So McDermott state that if you have T1 to Tn independent random variable, then taking value in some set of T, suppose there's a function f Tn go to R, then we have to find out C1. That's the most important part of this inequality. So I will explain what is T1 to Tn in our MCQ problem. So instead of thinking of 500 MCQ question as like a whole, without divided into 500 different trial T1 to T500. That is how you want to see this problem. So for each T1, what is the chances of what is the value of T1 to T500? It's literally just gonna be T1 Ti will equal to 0 if you get it wrong, and Ti will equal to 1 if you get it right. So every of our T, so that's every of our T. So our X is gonna be the F of T1 to Tn, for which we want to find the number of correct answer that we got. So the F here is gonna be T1 plus T2 plus 2T500. This F is not just about the sum. You can literally do anything else, even like T1 multiplied T2. It still applies. It's not just so small into just a sum, but it's literally, it can be any function. So the only thing that we have to care for is that how we can divide our question into the form of T to get the form of T. And then we will consider, so then we can evaluate our C. So what is our C in this problem? So the thing here, they say, suppose there's a function f, then C will be the maximum of the changes of f T1 to Tn compared to T1 to Ti minus 1, and then continue. So this means if you change 1 T, how big will the result gonna change? So if you change 1 T, for example, if our Ti equal to 0 here and our Ti here equal to 1, the maximum that it can change is just 1. In other cases, for example, if our F is equal to T1 multiplied T2, for example, to Tn, the maximum it can change is literally so big. It's literally the whole C. It's gone. So that's how we can evaluate C here. So for this question, I would say my C is gonna be 1. And it satisfies the two condition of is having a random T1 to Tn, and it also exists a C. That's why I can using this probability here. So our probability of x minus 100 bigger than 30 is smaller than exponent of, this is 230 squared over, this is like the sum of OC, so it would just be 500. So if I plug the number in like here, we will have the result of 0.05, for which the bound is way much smaller than the 75% that we just stated before. That's why I think that's why this concentration inequality is way much more effective compared to the Markov or Chebyshev. So, but the thing is like, if you're dealing with machine learning, you want an even sharper bound because distribution, if you're using moment generated function, it will always be exponent distribution. So we always know it's gonna be having this kind of shape, right? But what if I want to know if it's like this kind of shape or like it's even a sharper exponent distribution? So that's why we have an even better bound for which we call high dimensional concentration inequalities. So high dimensional concentration inequality, they have a lot of results, but if you happen to look more into graph theory field, then one of the most like foundation inequality that I have been seeing in like literally every paper I want to introduce here is Talagrand inequalities. So the Talagrand inequality know for a fact that your distribution will be exponents already. They know it's going to be exponent. They know it's going to be concentrated, but they want to know if it's concentrated or concentrated. That's why it's try to see your data set into a more geometric viewpoint. That is when you're not just gonna look at like if you remember how the other concentration inequality was looking at, it was looking at counting individual changes. Like if one changes, how much of your functions will change. But for Talagrand inequality, you're not just looking for that, but you're gonna divide it by the ratio of how much that one change is gonna change your variable in total. It's not just like how much it can change, but how much it changed comparing to like other changes. That's why it's a way much more like a way much more sharper parameter. So Talagrand inequality state that if X is a non-negative random variable, which you can say T1 to Tn, then there exists a constant C in R for which we have to find that changing the outcome of one chart can affect X by at most C's, for which I just explained for the McDiarmid. That is the same thing as here. And then the second one is the one that why Telegram is way much better than other concentration inequality is that for every X, if X bigger than S, then there exists a set of at most RS trial whose outcomes certify that X bigger than S. So this is so I will explain how this works. For example, if you flip a coin 50 times and you want to guarantee that your X is going to be more than 20, then how many times do you have like how many results that you have to see to guarantee that X will definitely be bigger than 20? It's going to be 20, right? Like you have to see the result of the first 20 to actually guarantee that your value of X will be bigger than 20. And then in that case, our R is gonna be 1 because our S is, so if this is in that problem, it's like X bigger than 20, then there exists a set of almost 20 trial that you have to see to guarantee that your X would definitely bigger than 20. So that's in that case, our R will be equal to 1. So that's how we can determine R. And once we have C and R, we can plug in our exponent here to find the sharper bounds of it. So I've got some recommendation of explaining why Talagrand inequality, it's like the application of it is really big. It's because if you study the study of graph, then the result of, because in graph random processes, it's always going to be exponent without doubt if you're using probabilistic method. That's why we want to find a sharper bound to have like because like for graph research, we just keep working and working until we find like a smaller running time, a smaller like chromatic number and stuff like that. That's why we keep wanting to get a sharper bound by time. That's why Telegram has been appearing into like a lot of graph research paper. So I want to apply it into one of the example today is on random subgraph problem. If you might or may have ever seen this kind of graph, then this is a random graph. This is a random graph. And why random graph is really important, why it's being used a lot, is because it's related to a field where you have to dealing with complex network and algorithm where you want to encounter for all the exceptions. That's when you have to use random subgraph. This one is kind of like if you have a graph G with n vertices and the probability of this is like n vertices, and then this is the probability that two vertices will have an edge. So that is how random subgraph works. So our problem today is to prove that if you have a G graph with V vertices, and you want to find a subgraph H in G such that the edge will appear with probability of P. And our goal is to prove that if X is the number of vertices that appear in H, then it will be concentrated around its expected value. If anyone don't really understand, just let me know if this like not really like really straightforward problem. But so our goal is to prove that the number of X is concentrated into its expected value, for which we don't really know. Well, there's a paper that proved that there exists like this expected value is like a square of n, but our goal today is just to prove that the expected value will be nearly this without actually knowing what the expected value is, just to make it a little bit simpler. So I'm gonna first talk about why other concentration cannot be used. First of all, turn off, like we said before, it had to be a Bernoulli random variable, but which the graph is not a Bernoulli random variables. It's not a sum of them. It's the chances that it's gonna appear is not a Bernoulli random variable. And then for Hofstadter inequalities, this is the reason why we're not gonna use it, because our number of T1 to Tn will gonna be V squared, because that is like the largest number of edges that will appear in your graph, in a graph, which is like a complete graph. So that's the number is way too high to be using here. If you're gonna divide them by V squared, it's gonna give you a way bigger bound than you want. So that's why this two thing is not gonna be applied into a high dimensional inequalities. That's just why it's not being used here. That's why we should use a Telegram bound. So I will try to find the R and the C that we just mentioned above about Telegram. So this is the first condition of the above, where we saying that like how much change one variable can change the whole X. So we see that like if we the problem is we have to set up our subgraph problem. So we have like a f of T1 to Tn, right? So what is our T here? So our T here is gonna be an edge. It's gonna be for each edge that appear there, right? So our n is gonna be V squared. It's gonna be f of T1 until T of V squared, right? So if you're gonna change one T, like Ti, for example, if you're changing them, then how much is f gonna change? So we have to come back here. What is our f? We have to define our f, right? So we want to find the number of vertices got contained in subgraph H. So for each edge, if it exists, then how much vertices it will be included in H? For one edge, we have two vertices. So the highest that T1 value can contain, or Ti can contain, is 2. if the edge appear in H, there will be at most 2 verses will got included in X. It can be also 1 in the case that 1 verses already be included in H and 1 other verses has never been included in H. That's when our T is gonna be equal to 1. And also our Ti can also be 0 if T does not exist in H. So that's why our changes will be at most 2. So our C here will be 2. And now we go into the second condition. So we remember that our second condition is that if X is bigger than S, then what is the RS triangle that we have to see? So for here, if we want to guarantee that there exists at least like 20 vertices that appear in graph H, then how many edges that we have to be included in H? Then the smallest number of edges that I have to see to guarantee that gonna happen, it definitely have to be like 20 edges. Because every 20 edges that exist in graph H, it will increase our graph of our X by 1, right? So if we want to see 20 verses in graph H, we have to see at least 20 edges to make sure that like our X will be at least 20. So that's why our RS trial will be RS trial will be S. So that's why our R will be equal to 1. So now we have our C and our R, we will just plug in our bounds, for which it's the expected value of X minus the expected value of X. This is like how much they changes. It will be smaller than the exponent of T squared divided by 32. This is 8 multiplied with CR squared. So our C is 2, our R is 1. So always, I think it's like C squared R. So that's why we have 32 here. And then we just plug it in. And if you're dealing with this kind of analysis in your research, you will just have to draw out the graph to see the changes of this bound and like the exponent distribution of this to actually see how much reliable it is of your expected value at this range of error. So is how you're gonna apply Telegram into graph theory. And I think that's the end of my presentation today. I hope you guys learned something of like concentration inequality, and if you feel interested into the graph field that I'm working with, I'm really more than happy to hear more from your perspective. Thank you.
Like related to the research that you do?
Yeah, I'm doing this. This is just like the basic part where we have to learn how to using this inequality. I'm working on like hypergraph. We are trying to find like a better chromatic number for edge coloring for hypergraph. That's what we're doing. It's like this is like a basic knowledge. I was trying to put up like a more like complicated, but I'm not sure how to explain it. So that's why I'm trying to like narrow it down. But
Are you working with the professor?
yeah, I'm working with
Which
it.
one?
He's like his name is Abhishek Dohan Hawan. He's like in math department. Yeah. If you guys, yeah, thank you. Oh yeah.
Is there a case where R is not equal to 1?
Oh, I think there's a lot of case. For example, if you're dealing with hypergraph, for example, if you want to make sure that every edge is gonna like have bigger than S, then our R will definitely not just gonna be 1, it will be the number of edges. Because hypergraph an edge does not contain like 2 vertices, but instead it contains like an n number of vertices in it. So that's the case of it.